Okay, so this is CET236 and we're live on...
So you're muted.
I'm muted still. That's no good. I don't think I'm muted on... That's the problem. I can see my my mixer telling me that the audio is going out to YouTube, but it's not going out to Discord. So I'll have to remember that. Thank you. So we're CET 236, last lecture session for the semester. Welcome again. So that's where we are. I think I've got the wrong number here on the homework. Let's just go and have a look at the assignment calendar, the live one. And yeah, it's homework 9 that's due. Just a reminder, I have to get all the grades in by May 21st at 5 p.m. I think. So just be aware of that. Yeah, so that's not homework. See if we can get drawing. That's actually homework 9. So there are all the topics we've covered. We didn't really get a chance to play with a multimeter or a real power supply, function generator or oscilloscope, unfortunately, but we've covered everything else. And as I think I've said before, one of the things that sorry, what's that? One of the things I think I'm going to continue doing that I wasn't doing before we went remote is using LT Spice, because I think using LT Spice is a good way of being able to look at some of the results of the lab on your own computers. So I think that's a good thing. So I'm going to continue to use that. Just a reminder, there are course evaluations available. So I think thank you to the 7 people who've currently submitted one. I appreciate the feedback. I'd like to get this ring that I see in terms of the response rate green, and it looks like, based on my capstone 1 class, that 50% is what I need. So I need another 6 of you maybe to submit, so I get a green.
Entering for course reviews.
Sorry?
I'm going to.
You're going to. Please do. So one of the, I think they're useful. I tend to pay most attention to the free form submissions. I pay attention when some of the numbers are low too, but my numbers usually don't get too low unless it's something that's beyond my control. But please spend a bit of time, and if there's anything you think I can do to improve either the material, my teaching of it, your understanding of it, whatever. If you've seen another professor do something else and that you would rather me do, if you've seen something on YouTube or Coursera or anything, let me know. I'm open to doing stuff differently if it helps learning. Right, that's what I'm here for. Okay, so there's that stuff. That's everything. So what I intend to do today is to go through that list. I'll start at the beginning and we'll take a few breaks. I'm happy to answer questions about homework. I'm happy to answer questions about labs. I haven't caught up with all the resubmissions recently, so I will have to do that. I'll try and do that later today, so that if you have made a request for a resubmission, then you will that resubmission will be available. But if I haven't responded to your submission, then it probably isn't available yet. And yeah, that's pretty much it. So I started the midterm 2s a little late. But we have 21 out of 25 done. I think I've got another 4 to do. So I think everybody is booked at this stage. And we'll see how we go. The final is available, and it's a little different from the midterm, but not too much. The main difference is this time I've given you numbers for everything, so you should be able to grind out your solutions. And yeah, this is just all the circuits on the final. So unless anybody has anything else of more pressing concern, I thought I would start reviewing the whole course and seeing where we get to.
Before we jump in, is there a PDF for the final available somewhere? Is that like on the same place as the booking, and I just happen to miss it?
So if you go into assessment, and somewhere down here, I think, somewhere, there's the final, then there should be a link with the final PDF there under assessment.
Oh, yep, I just missed it.
Okay, so yeah, so that should be available to you. That's got all the questions that I'm able to answer. I'm only going to ask you one question per topic, right? So each one has, in this case, 4 different things I could ask you, but I'm only going to ask you one per question.
Okie doke.
Okay.
Sorry to interrupt here.
No, that's okay. I'd rather get any questions out of the way rather than me just talking at you. Right? It tends to help things better than me just talking. So I'm sorry. Was there another question?
I was just gonna say, like, for the final, so since you put numbers in there, are you going to be changing those numbers, or is it going to be identical?
You have the final. This is what is on it.
Okay, got it. Yeah.
I'm going to ask you to be. I'm going to be a bit more pedantic about the final than I have been about the midterm. Right. So the midterm, particularly the second midterm, I've been mostly about process. Here I'm going to be both about process and about accuracy. Okay, because you have the concrete numbers to use, and no, I'm not going to give you new numbers for the outside of the final. Okay. So yeah, we'll see. So one of the things I'm teaching this course over the summer, and I've been toying. I don't know. I've been toying with the idea. The what's it called? Banner statement about the type of course it is online asynchronous. That means one way to do that is completely asynchronous, right? No interactivity. I wouldn't be doing this sort of presentation. And I don't think that's a good way to learn. Some people can do it, but most people do better with some interactivity. So I've been very tempted, and I'm not sure I'm going to do it yet, but I've only got a couple of weeks to decide. I've been tempted to run the course like, and you may not remember, I don't know whether how wide an audience it had, but I've been tempted to run the summer course like the Mystery Science Theatre 3000 as a watch party for the videos from this semester or last semester, and well, last time I videoed it, and that way I get to heckle myself potentially, and but we'll see. I might just do it like I did this semester, but we'll see.
Professor?
Yeah.
You still haven't graded Lab 9, right?
I believe there is a bit of a backlog, yes.
Okay, and another question. For the resubmission of, like you said, labs or homeworks, you go to the resubmission link, and then it's gonna start like I guess it starts like a kind of like a exam kind of thing because it says to begin.
Yep, exactly. So
when I click on it and then I choose what homework I want, oh,
yeah.
There you go.
Yeah, so there's you can select 2 labs and 2 pieces of homework. Remember, if you've already taken advantage of the late or resubmission after the deadline, then that will eat into that 2 and 2. But
because the deadline is the 15th, right?
yeah, I'd like to get as much stuff done by the 15th.
Okay.
I have to get everything in by the 21st.
Because every homework that you graded, it's on the blackboard, correct?
That's correct. Yep.
Okay. All right. Thank you. Appreciate it.
Yep. No worries at all.
Is there a deadline that we need to get those resubmitted by this week or next week?
Not really. Like I said, I have to get my grades in by the 21st. I need time to grade stuff.
Mm-hmm.
So
the sooner the better.
Sooner the better, but there's no real. It's not going to close once you've selected the resubmit and I've added you manually to be able to resubmit. There's no deadline on it. Okay.
All right. Thank you.
You're welcome. Okay. So let's, there's no other questions. Let's go back here and let's have a look at this list. And I'm just going to go make it new. Did I get that? Okay, so let's keep that up there, and so let's remember where we started this way back when, right? So let me just get my cropping is a little, just going to see where my crop is. There we go. Right, so we've got a I usually use the acronym VIPERS, right, to start with. I don't know, I can remember it a little better than some of the others. It doesn't include some stuff. It doesn't include well, it doesn't include C and F, but I think it's a good place to start. I can talk about C and F when I come to talking about Z, the impedance, right? So this is voltage, and the units are volts, and the symbol is V. I, despite, and I keep forgetting the etymology, the background of why it came out as I. I think it was a French scientist that came up with, but that is, well, let's not call it that, let's call it current, and we'll go for the full name. Amperes or amps is the unit, and the symbol is capital A, right? P is power, and the units that I use anyway is watts rather than horsepower. Horsepower is more fun for cars, but for the stuff I do, it tends to be electrical and tends to be watts, and the symbol is W. Right? E is energy, and the unit, it's an SI unit, right? So most of the units I'm using are international standard units, and that's a joule for energy, and capital J is the symbol. R is resistance, and the Z is impedance, and the units for both are ohms, and the symbol is a capital omega. It's interesting, I'm teaching data structures, which is a computer science course at another institution, and they use capital omega for something completely different. Okay, so there are the starting points, right? And then there's some connectivity between these, right? P equals IV. The power is the current times the voltage. Okay. Another thing I haven't, so I'd said over here that I haven't brought in farads for capacitance or henries, right? I also haven't brought in charge, right? So it's another thing. It's the if you integrate a current, you get the total charge, and the unit there is coulombs, and I should say it's charge, and the symbol is capital C. This power relationship, remember we've got this idea of polarities, right? And some of the devices we've been using dissipate power. So if this is a resistor and we have the current flowing in this way, and we measure the voltage this way, then in this instance P equals IV is the power dissipated, or the power consumed, right? But we also have other active devices. This is a passive device, right? And I've drawn it that way because there's really three sorts of devices that we've come across in this course that are passive devices, right? Resistors, capacitors, and inductors. So this polarity for current and voltage satisfies what we've called the passive sign convention. Right? So if a device satisfies the passive sign convention, then this is true. Multiplying the current and the voltage gives you the power dissipated. If the device doesn't satisfy the passive sign convention, either the current's going the other way, or the plus and the minus on the V are swapped, then the power you get from multiplying the current and the voltage is the power generated or the power provided. Okay, so you've got to be sure about the passive sign convention. The other relationship that we've looked at, right, is the relationship which is Ohm's law, right? V equals IR or V equals IZ. And again, these hold provided your device satisfies the passive sign convention. If the passive sign convention doesn't hold, right, so this, then you get a different Ohm's law. You get V equals minus IR. And that's why the bulk of the mistakes that I make and the mistakes that you make are to do with signs, whether things are flowing one way or the other, or whether the voltage is measured one way or the other. So that's why I spent a reasonable amount of time early on in this course talking about the passive sign convention. Okay, so I've talked about those things. Let's talk about, and I've lost it already. Let's talk about, and I'll go back and cross those two off again. Let's talk about series, parallel, and combination circuits, right? So remember that if we have two, and I'm going to use the term impedances for now, because we know about impedances. It could be a resistor, but it could be an inductor or a capacitor, right? So we have Z1 and Z2. We have current I flowing in. We've got VZ1 and VZ2, so that now this current and these voltages are satisfying the passive sign convention, right? So the current is flowing in through the positive side. And what we want to do is we want to turn that into a single equivalent impedance. With a known voltage and obviously the same current. Excuse me, my throat's getting a bit scratchy. Okay, so how does that work? Well, the way it works is we know from Ohm's law that VZ1 equals I times Z1, and VZ2 is equal to I times Z2. Right? And we know that VZ equivalent is equal to VZ1 plus VZ2. Right? If we start off here, we go up by VZ2, then we go up again by VZ1, so we just add those two. And I don't know why I made that a subscript. Let's write that correctly. So that should be I Z2. Right, I times the impedance. So then we get right, so that VZ equals I Z1 plus I Z2, and I don't know why I keep making that a subscript, I shouldn't be. And so that's going to be I times Z1 plus Z2. And from that relationship, we should be able to see that this is just the equivalent impedance. Right, so the equivalent impedance is for series impedances is just Z1 plus Z2. Okay, let's talk about parallel. Right, so again we've got our impedances, and I'm going to be bold and not draw them physically parallel. Right, but believe it or not, those two, Z1 and Z2, are electrically in parallel. Remember what that means? That means that, so actually let's go back and remember what series means. Series means that two devices uniquely share a common node. And remember, a node is an area of constant voltage. Okay, so this is a node. In fact, this whole thing here is a node. And so that's an area of constant voltage which Z1 and Z2 share with nobody else. Okay, so now let's think about what parallel is. Parallel is two, or sometimes more, but two devices are connected between the same two nodes. Okay, so let's just check that out. So here's one node, and both Z1 and Z2 are connected to it at one end. And here's another node, and both Z1 and Z2 are connected to it at their other ends. Okay, so these two devices are in parallel. Because they're in parallel, because they're connected between the same two nodes, this time instead of having the same current flowing through them, they've got the same voltage across them. Right? So here, right, and we've got IZ1 and IZ2. So now we've got that I for Z1 times Z1 equals I for Z2 times Z2. And what we want to get to is we want to say that that is equal to I total times, and let's just call it Z equivalent like we did before. Now I haven't yet in this summary talked about Kirchhoff, right? So let's just take a little bit of a break and talk about Kirchhoff, right? Kirchhoff has two things we're interested in. There's a voltage law and there's a current law. Right? And the voltage law and the current law both say essentially the same thing, except one is about voltage, and that one says that the sum of the volts around a circuit is zero, and the current law says that the sum of the currents into a node is zero. Okay, so looking at the current law, then we can say down here that I total is equal to I1 and remember that there's two ways to talk about the current law, right? One way is to say the sum of the currents into a node is zero. Right? That's one way to say it. Another way to say it is to say the sum of the currents into the node, into a node, equals the sum of the currents out of the node. And that's what I'm doing here, right? We've got I tot flowing into the red node, and we've got I1 and I2 flowing out. So the way the first statement would write that equation would be I tot is flowing in, and because I1 and I2 are flowing out, we would just negate them. They're the same equation, it's just one of them's got all the ingoings on one side and all the outgoings on the other, and the other one uses negation. Okay, so we've got, let's see if I can move this along a bit. So we've got I Z1 plus I Z2. Sorry, it's not equal, we just want times Z equivalent. So how do we do that? Well, so we've got those three equal, and I'm just trying to think what the best way to do this is. Well, let's try this. So what we can do is we can say that I Z1 is equal to Z2 on Z1 times I Z2, right? Because I've got I2 Z2, I just divide both sides of this equation by Z1 and I get I Z1 in terms of I Z2. And then I can probably put that in there. Don't know whether that helps at all. Does that help at all? Right? I'm trying to work towards what we know this is, right? So that is I don't know. Let's just try it. So we get Z2 on Z1 plus 1 times IZ2 times Z equivalent equals, and we've got IZ1 Z1, or it equals IZ2 Z2. Okay, and then what we can do is if we take this piece and this piece, right, we can cross out, we can cancel the IZ2s on both sides, and then we're just left with Z2 on Z1 plus 1 times ZEQ equals Z2. Right, so ZEQ equals Z2 divided by Z2 on Z1 plus 1, and now we can multiply top and bottom by Z1, right, and we get Z1 Z2 on Z2 plus Z1. And believe it or not, that's the same as that, right? We can now just divide top and bottom by Z1, Z2, and that gets us our parallel equation. Okay, so that is series circuits and parallel circuits. And all I'm going to say about combination, series and parallel is that you can, provided they are in series or provided they are in parallel, you can replace the series resistors with its equivalent, or you can replace the parallel resistors with their equivalent. Okay, so that's combination, series and parallel. And I've talked about the passive sign convention, that the current has to flow into the positive side of the voltage polarity definition. I've talked about Ohm's law, right? V equals IR down here. I've talked about Kirchhoff's voltage law and Kirchhoff's current law. Oh, sorry, I didn't realize. Tonight's homework problem 3. We can do that. Let me just finish up a couple more things, Giovanni, and I'll address homework problem 3. I think several people have had problems with that, and the issue is that they're including resistor 4 in the initial condition calculation, and it shouldn't be but I'll have a look shortly. Okay, so yes, so one thing I want to re-emphasize about Kirchhoff's current law and Kirchhoff's voltage law is, even though I've written them down mathematically, they're really a physical constraint, right? The if you could break Kirchhoff's voltage law or break Kirchhoff's current law, you would be a millionaire, because you could create power out of nothing. You could create energy out of nothing. And while that would be wonderful, it's not physically possible. Okay? So that's, and just remember the voltage law, the sum of the voltages around a loop. Ooh, we haven't defined loop. Let's go define loop. All right, so this sum is around a loop. And a loop is a closed path around a circuit that doesn't cross itself. Right, and closed means that it begins where it ends. Right, so there's no. So that's what a loop is. And we need to talk about a mesh at some point, but let's not go there just yet. So that was, and we talked about a node. I think I defined a node. Okay. Next up is resistance from resistivity and shape. and resistance change with temperature, right? And I hope you remember the Apatosaurus, right? Remember, this is a, I don't know, hard rubber, I think we decided. And from the tip of his tail to the tip of his nose, we could possibly approximate him by a series of 3 cylinders, right? And let's just scroll down. So remember the Apatosaurus, right? So let me just quickly do a really bad drawing of an Apatosaurus. That's so bad. Right, and I probably should have drawn some back legs as well. But the idea is that you could approximate this Apatosaurus with 3 cylinders, and apologies for my lack of straight line drawing ability. Okay, and remember the resistance of any of those is equal to rho L on A, where that's in ohms. So rho is the material property of resistivity. L is the length, and A is the cross-sectional area. And remember, so right, so this is A1, this is L1, this would be A2, this is L2, and if we had that would be A3, and this length here would be L3. Right, so our equivalent circuit for the Apatosaurus would be 3 series resistors, and the numbers, assuming the Apatosaurus is made out of the same thing over his whole length, then this would be rho L1 on A1, rho L2 on A2, rho L3 on A3. And that resistivity is a material property, right? It changes depending on what the material is. If it's made out of copper, that's one thing. Obviously, copper doesn't have much resistance. If it's made out of carbon, that's something else. If it's made out of hard plastic, like the Apatosaurus, it's made of something completely different. Okay, so that's resistance from resistivity and shape. Wish I could draw straight, that would be wonderful. And then resistance change with temperature. Right, so because when temperature changes, that makes the molecules in the material bounce around a little differently. So we're going to expect a change in resistance from the nominal resistance, R nom, right? So we get our resistance at a given temperature T from this equation, R nom times 1 plus alpha times T minus T nom. And usually this is 21 degrees Celsius. And note that it's usually, this number is the temperature coefficient and it's in per degrees Celsius. So you need to make sure you get all the units to match. It's possible to do the same thing in Fahrenheit or Kelvin or whatever your favorite temperature measurement system is, but you need to do conversions between them. And most of the information we have is in per degrees C, so you need to convert everything to Celsius. And once again, that alpha value this time is a material property. It changes depending on the type of material the resistor is made out of. Sometimes alpha can be negative. So if you heat up some material, it gets more conductive, it gets less resistive. Some material, if you heat it up, it gets more resistive. So alpha is positive. Depends on exactly which material, whether alpha is positive or negative, and how big a change it makes. Okay, so we've gone through resistance change with temperature. So what I'll do is I'm just going to cover voltage dividers and current dividers, and then I'll go and maybe we'll have a bit of a break, and then when we come back I'll deal with Giovanni's question about problem 3 for tonight's homework, and then I'll continue going through this list. Okay, so voltage dividers. Right, remember what a voltage divider is. A voltage divider is something like this. Right, where we have a V in, and I probably should have drawn those as impedances rather than resistances, but let's just go with the flow. Right, and a V out. And the relationship between V in and V out is that V out is equal to R2 on R1 plus R2 times V in. Okay, and from our derivation of series resistances that we did before, you should be able to derive that equation. So then the other one is current dividers. So this is voltage dividers. And the other one is current dividers. And remember, current dividers are trickier, right? Because here we get that the total current, well, we get that the current through R2 is equal to R1 divided by R1 plus R2 times the total. Right, so it's the, here it's the current, it's the resistance in the other branch, whereas in this one it's the resistance where we're looking at it, right? So that's why current dividers tend to be a little bit trickier, because you've got to look at the current in the other branch, or you've got to look at the resistance in the other branch. And it gets even trickier because if you have more than one resistor in parallel, right, and you want to find out what this current is, let's call that I4, right? The other branch is the other branches. So what you've got to do is you've got to basically find the equivalent resistance of those three other branches in parallel before you do the current division, before you use this equation. Okay, so there we go. We've got voltage dividers and current dividers covered. So I've been going for a little bit under an hour, and I don't know whether it's not a third of the course, it's about a quarter of the course, right? So I'm hoping that by the end of today I will have covered the whole course in about maybe 3 hours, maybe 2.5. So hopefully it's not too quick, but hopefully you've learnt something along the way. Does anybody have any questions so far about what I've been saying? Okay, if not, let's take a quick break, and let's make it a 10-minute break, and when we come back I'll talk about the homework, problem 3 in particular, and then I'll continue with my review of the course. Okay, and we're back. Let's have a look at tonight's homework. So I'm going to go to webwork.
I think you're muted.
I'm still muted? Yeah. Same mistake as earlier. Thank you. Okay, so we're back and let's have a look at tonight's homework, which is the transient one, particularly I think yeah, particularly what do we got? Is that that was from last week. So problem 3. So let's have a look at the homework, and the homework is transients. So let's go here and go to transients and problem 3. Okay, so there's my version of problem 3, and let's just grab the screenshot and take it over to OneNote, and I'll just add another page. And let's insert that screenshot here so we can have a look at it. If I can figure out where my screenshots got to, there it is. Okay, so it's a transient problem, right? And that means we've got to find the initial conditions and we've got to find the final condition. So time minus infinity, or just before 0 usually, and then time plus infinity. So let's have a look at it. So before t equals 0 seconds, the switch is closed. At t equals 0 seconds, the switch opens. And we've got a 40 volt power supply, and R1 is 2500 ohms, R2 is 1000 ohms, 1 kilo ohm, R3 is 2000 ohms, R4 is 2500 ohms, and my capacitor is 750 microfarads. Okay, so let's redraw it using just having a look at the initial condition, right? So the initial condition, we definitely have the battery in there because it said the switch is closed. We have resistor 1, we have resistor 2, we have resistor 3, right? So R1, R2, R3. I wish it had changed back to the dot so I could see it a bit better. Right, so there's our 40 volts, not 60 volts. I think somebody was helping the other day had a 60 volt supply. Now, the rest of this circuit, because we've been at steady state for a long time, really, the rest of this circuit looks like this. Right? The capacitor is not going to let any current flow because remember I equals C dV dt, and dV dt, the rate of change of the voltage across the capacitor just before that switch opens is 0. So the current flow through the capacitor is 0. So the current flow through resistor R4 is 0. So we don't need to deal with anything around R4 or C in the initial case. Okay, so our first example, our first circuit, and remember this is still VC at time 0 minus, but VC, the voltage here is the same as the voltage here because there's no current flow. There's no current flow, there's no voltage drop across R4, so it's like the open circuit voltage that we looked at when we were talking about Thevenin and Norton circuits. Okay, so then, well, what does that give us? Well, we can redraw that circuit again, and we can say that, okay, we've still got the power supply, and we've got R1, but we can just draw it R2 and R3 as a single equivalent resistance with R2 in parallel with R3. And then this voltage here is our VC at time 0 minus. And for mine, so what's that? That's, I should have fired up MATLAB. Let me fire up MATLAB. So what's the, it stopped going again. Let's try again. Really wish they'd fix their software. Right, so our so that's still 40 volts. That one up there is still 2,500 ohms. But this one is R2 in parallel with R3, which is 1,000 in parallel with 2,000, which equals, if I can figure out where MATLAB got to, there it is over there. Thinking about it. There we go. There we go. Right, so R2 was 1,000, R3 was 2,000, and R equivalent is 1 on R2 plus 1 on R3. Which is 667 or 666.7 ohms. To 4 significant figures. Okay? So then we can say that our VC at time 0 minus is just going to be 666.7 divided by 2,500 plus 166.7 times 40 volts, which I can't do in my head, so let's go back to MATLAB and see what MATLAB tells us it is. So it's REQ divided by REQ plus 2,500 times 40. So VC0 is 8.42. Okay, so that's the initial condition. and the initial circuit. The final circuit is with the switch open, and again, because that switch is open, no current's going to be flowing through R1, so we're just left with those 3 resistors, right? So our equivalent, so the final condition is going to look like that. But again, we've got to remember there's 3 numbers we need. We need the initial condition, we need the final condition, and we need tau, the time constant, right? And tau is RC. Okay, so well, let's do the final condition first, right? So this is effectively what's happened. There's no power supplies at all. There's no current supplies. There's no voltage sources. So that's going to tell me that the voltage across the capacitor at time infinity is 0 volts. Okay, and remember the thing we're trying to fit is Vc as a function of time is K1 plus K2 e to the minus t on tau, and there's our tau there. And so that says that Vc of 0 equals K1 plus K2, Vc at infinity equals K1. I think that's right, K at infinity, it's e to the minus infinity, which is so small it's 0. So that means that, that tells us that K1 is 0, and that combined with K1 being 0 tells us that K2 is 8.42 volts. So then we can say that Vc of t is 8.42 e to the minus t on tau. Now the question is, what's tau? Well, tau is RC, and that R is, remember, the Thevenin equivalent resistance. So the Thevenin equivalent resistance of R4, R2 and R3 is going to be R4, don't know why I wrote a 4 instead of an R. R4 in series with R2 in parallel with R3. Okay, and R4 is, what do I say, is 2500. Yeah, R1 and R4 are both the same. Right, so our RTH, I think we did R2 in parallel with R3 before. Right, so it's going to be 3166.7. So our tau and what was C is 750 by 10 to the minus 6. I think that's right. Let's just check that I can do the numbers in my head appropriately. So REQ plus 2500. Yeah, there's our number. And I need to multiply that number by C, which is, I think, 750 microhenries. Sorry, microfarads. All right. So our tau is 2.375 seconds. So I can plug that back into here, so it should be 8.42 e to the minus t on 2.375. Let's just see if that works. I don't know whether I've got enough significant figures. So it's going to be 8.42 times, I don't know whether it wants an exp minus t on 2.375. I think that's right. Let's just check and I'll show the answers. Yep, it looks like that's correct. Okay, so I possibly could have given a few more significant figures, but that one's okay. And the next question is, what's the output voltage? Where's the output voltage? Well, the output voltage is here, right? And they only want the output voltage for time greater than 0. So let's have a look at the circuit again, right? The circuit is R2 in parallel with R3, and that is our output voltage, right? And then we've got our VC here, right? So that's R2, R3, and R4, and the relationship between VC and the output voltage is just through a voltage divider, right? So the output voltage is just something like that, I believe, right? So it's going to be, the tau is going to be the same, it's just the number at the front that's going to be different. So let's see what the number at the front should be. So that's going to be R equivalent divided by R equivalent plus 2500, I think it was, times, now what was our VC0? Right, 1.7729. So that means my output voltage is 1.773 e to the minus t on 2.375. And I think that's what this one said. Did it say that? Yeah, so I can type that 1.773 times exponential minus t on 2.375, and we can check our answers again, and we got everything correct. Okay, any other questions about the homework that's due this evening? Okay. Problems 2 and 4. Okay, we can do that. So let's go. I'm just going to click next problem. Let's have a look at problem 4 first. So before t equals 0 seconds, the switch is open. Assume no current flows through the inductor before time t equals 0. At time t equals 0, the switch closes. Okay, and then we want an expression for IL. And now this one's a bit tricky and it's not properly stated, I think. I think they want VR rather than VO from the looks of things. So let's have a look at how to do this one. Again, I'll just take a screenshot and pop that over here. And this is problem what do they call this one? Q3. So transients HWQ4 is what we want. And we'll just shove that screenshot in. So for the initial condition, right, we're already good, right? So IL at time 0, 0 minus, is 0. Okay, so then the question is, what is IL at time infinity? So that's the initial condition, and this is the final condition. The final condition, we have the switch closed, right? So our circuit looks like that. And remember, in the final condition, everything's in steady state. If everything's in steady state, then L di dt, the voltage across the inductor, is 0, right? Because the current through the inductor is not going to be changing. There's no time varying voltages here, at least not on the longer term. There is in the transient phase between time 0 and time 5 tau. Remember, 5 tau is the long time. That's the time it takes for a transient to get within 1% of its final value. Okay, so if the current flow is constant and there's no voltage across VL, then all we have is the voltage source and the resistor. Right, so that means we just have V on R, so 10 volts in my case, on 10 ohms, which is 1 amp. So again, our general form of our current is K1 plus K2 e to the minus t on tau. And here at infinity, that's equal to K1, and that's equal to K1 plus K2. Right, so that means we know that K1 is 1, and that means we know that K2 is minus 1. Right, so that means we can plug those in, so that's going to be 1 minus e to the minus t on tau. Now we've got to figure out what tau is, and remember tau for this sort of a circuit is L on R. right?
Professor, why K2 is equal minus 1?
Well, we know that K1 is equal to 1, right? We also know that in the initial condition, that's when t is 0, so that means the general form of this at time 0 is K1 plus K2 equals 0. So if K1 is 1 and K1 plus K2 is 0, that means K2 has to be the negative of K1, right?
Okay, yeah.
Okay, and then our L on R, well, L is 2.5, R is 10, so that's 0.25 seconds. Right, so we can write out our full expression, 1 minus e to the minus t on 0.25, or we could rewrite that as 1 minus e to the minus 4t, and that would be in amps is the units. Okay, let's see if that works, just in case it doesn't. Right, so 1 minus exponential minus 4t. And let's just check the correct answers in case I'm wrong. Yeah, it lets me do a 4t, and it still puts it like that, but it lets me do a 4t. Okay, and then let's have a look at what the next piece is, the output voltage. Well, the output voltage is just going to be Ohm's law, right? So we take our current and we multiply it by the resistance, which in this case is 10 ohms. So we just multiply everything by 10. So it's going to be, I think, I'm assuming V out equals VR, right? So it's just going to be 10 minus 10 e to the minus 4t. And now we're in volts. I think that's what it has. Yeah, that's what it has. So I can just take my answer from the previous one and put a 10 and a 10 there. And I can check my answers. And we're all good. Okay, so that was question 4. You also wanted question 2, so let's go back a couple to question 2. So the switch below moves from left to right at time t equals 0 seconds. So we're going from an initial condition. Again, we're assuming that the switch has been in place for a long time before we get to time 0. So that means there's no voltage drop across the inductor. So the only thing that signifies as far as the current, the initial current is concerned, is the resistance and the voltage. So let's just grab that. And this will be transient homework. Oops. And this is Q2. And it looks like it's stopped saving the text in the appropriate place. So I'll just kill that, and I don't want to print out. So I think this is question 2. Okay, so as I said, the initial current, IL at 0, is just going to be the voltage, which in this case is 14 volts, divided by R1, which is 2000. So what's that? That's about 7 milliamps, right? And then when we swap over, we've got no power supplies. So after a long time, our final, again, this is the initial condition, and this is the final condition. Right, so after a long time, there's going to be no current flowing, right? Because there's nothing to push it around. There's no voltage source, there's no current source. So at time infinity, we get that. And again, our IL as a function of time is K1, the generic form, plus K2 e to the minus t on tau. And K1, so at time infinity, that's equal to K1. So that means K1 is 0. And that means K2 is 7 milliamps. And it's just a matter of figuring out the tau. Again, tau in this case is L on R, but remember it's the Thevenin resistance. In this case, we have R2 in parallel with in series with R3. So RTH is just 3 kilo ohms because they're in series. And it's going to be what, 2.5 by 10 to the minus 3, which is L divided by 3000. And I'm not going to do that in my head. I'm going to go to MATLAB to do it. Right, so 2.5 times 10 to the minus 3 divided by 3000. And that's, it's quite small. That's 0.833 microseconds. Right, 0.833 microseconds. Right, so that means our final answer here, K1 is 0, it's going to be 0.007 for the 7 milliamps, and minus t on 0.833 by 10 to the minus 6. And let's see if that works. So that's 0.007 times exponential minus t on 0.833 by 10 to the minus 6. I don't know whether that's going to work. It might need me to put things in a better format, but it's okay with that. Okay, so that's question 2 and question 4 and question 3. I also had a question about the peer review. So peer review was completely optional, and I noticed only a few people took me up on it. So let's have a look. Right, so where is it going? Peer review. Right, so the idea here is to not have me grade your assignments, but to have everybody else grade your assignments. And I don't know whether... Oh, that's right, I haven't ever used this option in Blackboard before. So I've got to go in here and submission date is ended. Let's have a look. Right, so they're the submissions, and we got 1, 2, 3, 4 people submitting, and then the aim is that you evaluate each other's, and we've got 1 in progress submission. And I probably shouldn't have showed you that. That's showing you who's evaluating you. I think what happens is you have to evaluate 2 people's assignments, and I think I set up a simple grading rubric for you to do that. And again, the aim is not so much whether you get the questions right. The aim is to see how other people do it and maybe learn a bit from that. Okay, so that's the peer review. Like I said, I haven't used this before. I think I'm going to use it more now that I've seen how it works. I didn't. I should have started using it way earlier in the semester, I think, with maybe some simpler problems. Okay, any other questions about the homework or assessment or labs or anything like that? You will notice I do have a backlog of stuff I need to grade. I forgot actually that I forgot to mark Ryan's midterm. I'll get to that shortly, Ryan. And then there's homework and various labs. And then the other thing I need to do yet is deal with the resubmissions, right? So right, there's looks like 10 people have either thought about requesting resubmissions or have actually got resubmissions. And I don't believe I've gone through yet and started making those available. What will happen once you've given your submissions, or once you've selected your submissions, is you will, those assignments or labs, homeworks or labs will reappear within Blackboard. At the moment, most of them probably aren't there, right? So we can go into the student preview mode. And it looks like the only things I can see now are the homework which is due this evening, and then the other stuff that's outstanding, and I obviously haven't done an oral. And then similarly for the labs, there's nothing due for the labs. It's unless you've asked for a resubmission. Okay, so they will reappear once I have to go in and manually add you to be able to resubmit them. So it'll be after the lecture today. Okay. So let's go back here and see where we are. Jonathan, as I said, once I add you to the labs manually, they will reappear in Blackboard, including the lab sheets. Right, so you'll have to wait until after I've manually added you to be able to resubmit, and then you'll be able to see them again, including the PDFs. Okay. Okay. Let's go back with this. So what I thought I should do before we go on with actual circuit analysis stuff is just quickly talk about linear algebra and complex numbers. Right, so you should have access to Professor Broderick's book, and it's got some nice stuff about both of those things. Right, so the idea with linear algebra is that you've got a system of equations and you want to be able to find numbers, in this case x, y and z, that makes all three of those equations true. Okay, and it's just there's a few ways you can solve that sort of equation. One of them is by substitution. Right, so we can take one of those, or we can take those equations and we can rewrite one of them, possibly, and get one variable in terms of all the others, and then just substitute that back into one of the other equations. So here in this example, y and z are already in terms of just x, so we can just take those two equations, right? Now let's just go back to thinner and substitute y and z into that equation. That'll allow us to solve for x, and once we've solved for x, we can just put x back into these two equations to find out what y and z is, and that's called substitution. Right, another way to do it is a technique called elimination. And here we treat the three equations by adding or subtracting multiples of one from the other in order to eliminate one of the variables. Right, so here we've got those same three equations but rewritten so that x and y and z are on the left hand side and the constants are on the right hand side, and then we can just add equation 6.1 to equation 6.2, and because x is negative in one and positive in the other, that will eliminate x from the equation. Similarly, we can then scale 6.2 and subtract it from 6.3, and again we eliminate x from the equation. We get another equation. Now we've got two equations in two unknowns, which is a little easier to solve, but then we can subtract those two equations from each other and get an equation that just involves y, and from just having y we can then back substitute into the other equations to find x and z. Those techniques work. The only problem with them is they tend to get a bit error prone once things get a little bit more complicated, right? Once we start getting resistances in kilo ohms or impedances in complex numbers, they tend to get a bit more complicated. So that's why I've introduced using matrices, either MATLAB or your calculators, to do a matrix inverse. Right, and remember at least the MATLAB equivalent of the way you would do it in your calculator is to create an appropriately sized matrix with all the coefficients of each of the equations in it, and then just apply the RF function to that matrix, and then the RF function outputs an identity matrix in the first square part, and then the answers to X, Y, and Z in the last column. Right, and within MATLAB, there are lots of ways you can use to solve the equation. If you have your numbers in the coefficients of X, Y, and Z in A, and the constants in B, which is what I've done here and here, then you can use one of those four techniques in MATLAB to find the solution. And remember, for TI-83 and TI-84 calculator users, there is a slight problem once we move on to impedances, because impedances now introduce complex values to things. The TI-83 and TI-84 calculators won't allow you to do RF on matrices with complex values. However, all is not lost. You can still do solve the problem. It just makes the problem a little bigger, because you have to replace every complex, and in fact non-complex, number with a 2x2 matrix of that form. So A, the real part of the number on the major diagonal, and then the B is on the off diagonal, and in the top right element the B is negated. Right, so in the example we have a complex matrix, and so we have to take our 7 minus 10j and turn it into a 2x2 matrix. So instead of having an augmented matrix that is 2x3, the thing that we feed into RF, now it has to be a 4x6 augmented matrix. Works exactly the same way. The result of RF is still the identity matrix, but now we have the result in two columns, and you should see the same structure, right? On the major diagonal, those two numbers should be the same, and in the off diagonal, those two numbers one should be the negative of the other. But basically this fifth column is the one that you need. So that's the real part, and that's the imaginary part. I have been doing some of them. If you want to do more problems, we can have a look at the peer assessment problems and see how they come out. I'm happy to do anything you want, Stephen. Okay, so that's talking about linear algebra, and you should be pretty confident in doing linear algebra either in MATLAB or on your calculators now. The other piece I wanted to talk about is complex numbers. So again, let's go to the textbook, or Professor Broderick's notes really. It's not technically the textbook. And I've forgotten which chapter it is. Thought he talked about complex numbers, complex power, transients. I thought he had a section about complex numbers. Maybe it's not a separate chapter. Phasors, that's it there. So we want 137. Okay, and remember, and I'm going to use the term phasor, right? A phasor is a representation of a complex number using effectively polar notation, right? It's a magnitude and an angle. So on the screen now we have the number 1 with no imaginary component. So its magnitude is 1 and its angle is 0 degrees, right? And then we can look at the same magnitude 1 phasor, but this time the angle of 45 degrees to the real axis, and that means the projection of that onto the real axis is 1 on root 2. Okay, 0.707 to 3 significant figures. And so that's what the right hand graph is showing, that at 45 degrees we've dropped down to 707. And then once we're fully imaginary with our unit phasor at 90 degrees, then the projection onto the real axis projects down to 0. So we're at 0 at 90. And similarly, when we have our angle of 180 degrees on our phasor, our unit phasor, it's still only unit length of 1, but now it's in the negative real axis direction. So we get a -1 as the projection onto the real axis. And then we can go to 270 degrees. Again, purely imaginary, but this time in the down direction or the negative direction. Okay, so that is effectively what we're doing. The plots on the right are showing the projection of a unit phasor onto the real axis for the given angle on the x-axis here. Okay, and so remember, with normal real valued numbers, we're just interested in a number line. But once we move to complex numbers, we're interested in numbers on a 2D plane, rather with a real axis and an imaginary vertical axis. So there's 3 ways we've looked at to, or maybe a few more, but right, if we have A plus JB That's one way to write, and it's a rectangular form. We could also write it just as Cartesian coordinates, right? X and Y coordinates. We could also write it as the phasal form, the polar form. And related to the polar form is the exponential form, right? Re to the j theta, because e to the j theta is Euler's formula, which is cos theta plus j sine theta. Okay, and then the rest of this just goes through polar, rectangular, and exponential form. Right, and the if you want to convert from rectangular form to polar form, then you can just do this. But remember that arctan, or tan inverse, tan to the minus 1, usually only works in the first and fourth quadrants. It doesn't work correctly in the second and third quadrant. So you've got to add something to the answer you get for theta if you're just using the one argument arctan function. Okay. Any questions about linear algebra or complex numbers?
For the final questions on, I think it's like the first problems with like converting, like using those sort of things. Can we use MATLAB for that, or should that all just be like done kind of like the ways we learned?
Not quite sure what you mean. You can use
like I'm looking at it right now. So like when you like add v1 and v2 and they're both like cosine functions, like you could do that like kind of easily in MATLAB. I was just wondering if you want me to like write it out when submitting it.
I do. I do want you to write it out. But using MATLAB to actually get the final answer is perfectly okay, right? I've used MATLAB all the way through. I would have preferred to use a calculator, but I couldn't get it to. I should see about getting the simulator working again for the calculator. But no, it perfectly okay. I do need to see the intermediate steps that you use, though. Okay.
Okay.
And one way to do that is, rather than just writing down the answer, is also using the MATLAB code, right? That, to me, provided you're using appropriately named variables in MATLAB, that's as clear as writing down the working on a piece of paper.
Okay, so like sending you the code.
Yeah, putting in the code. Whatever works.
Oh, and when you mean like code, like for example, like transients, the written out function that you have with like an exponential transformation, like with exp and stuff like that. That's kind of what you mean.
Yeah, exactly. Ryan, I think you're unmuted.
Okay, thank you.
Yeah, no worries, Dylan. Okay, let's continue on. I'm going to go for another 20 minutes, then we'll have another break, and we'll see where we are then. Okay, so mesh analysis, nodal analysis. So I suppose we should now define what a mesh is, right? Remember, a mesh is a loop that doesn't cross a branch, and we've got to define what a branch is. A branch is a circuit element. And let's just draw something to try and make the distinction clearer. Right, so if I have something like this, this is a mesh, this is a mesh, and I'll draw it on the inside so you can see where it cuts, right? I cut there. And I cut there. Let me just kill that. Right, so this red one is only a loop because it cuts that central impedance. Okay, so then let's talk about mesh analysis. Mesh analysis, nodal analysis, superposition, Thevenin and Norton approaches. They're the algorithms, the systematic approaches to solving circuits that we've used in this course, right? So mesh analysis is one, define the meshes. Right, and make sure you pay attention to the passive sign convention. 1A, see if we need supermeshes. Okay. Write down KVL, Kirchhoff's voltage law equations, for each mesh, and if there's a super mesh, there's going to be a KVL plus a KCL. Okay, write KVL equations in terms of the mesh currents. In step 2, we probably could have just done, you know, VR1, VR2, etc. This is explicitly saying we need to write it in terms of I1, I2. Distribute and group like terms. And solve. Probably using RF for preference. You can use the other techniques, elimination, substitution. They just tend to be more error prone. Once you've got the equations down, putting it into RF and getting the right answer is usually more likely than continuing with solving the circuits manually. Okay, that's mesh analysis. Let's get a... So nodal, oops, we want red. I thought I'd selected red. Nodal analysis. Remember, a node is an area of constant voltage. So first thing you do, define the nodes. Step 1A, see if there are any supernodes. And just remember, a super mesh happens when two mesh currents flow through a current source. Right? And a supernode is when there's a voltage source connected between two non-reference nodes. Okay, so we've defined the nodes, and then we write down KCL equations. Well, actually, it might be better. Let's do another step before that. So we write down the individual device currents in terms of the node voltages, and that includes direction. Then we can write down KCL equations. And if there's a supernode, then we have a KCL for the supernode and then a KVL for the voltage source. And then we distribute in group-like terms. And like terms in this case means the coefficients of the different voltages, the unknown voltages. And then we solve. And just remember, for mesh analysis, if we've only got one mesh current flowing through a voltage source, through a current source, that's a freebie, right? We immediately know what the current is, what the mesh current is. Similarly, for a supernode, if we have a voltage source connected between the reference node and another node, then that's another freebie. We immediately know the node voltage. Okay, so that's nodal analysis. And then superposition. Right, so this means, this is basically using the idea that any independent source has the same effect on the circuit regardless of the existence or otherwise of other independent sources. And they have to be independent. Right, and what that means in terms of an algorithm is, in turn, replace all other sources, other independent sources, with their ideals. Right, and remember the ideal for a voltage source is a wire, and the ideal for a current source is an open circuit. Analyze the circuit. And the result is some values from each smaller circuit problem. Okay, so that's superposition and Thevenin and Norton's theorem. Let's change colours. Let's go with green this time. Right, so Thevenin says I can replace any circuit with just a single voltage source and a series resistor or a series impedance, in fact. And there were three approaches we looked at to find RTH. One of them was the equivalent resistance. Approach. One of them was the open circuit voltage short circuit current approach, and the other one was the applier voltage approach. The equivalent resistance approach can't have any dependent sources in it. The open circuit voltage short circuit current approach has to have at least one independent source in it. And the applier voltage approach doesn't have any constraints. Now the problem with that is these all only get you RTH. You still need to find the Thevenin voltage, and usually that means you've got to at least do the open circuit voltage, because the open circuit voltage is the Thevenin voltage. And then Norton is very similar, but instead of a voltage source and a series resistor, we can replace any circuit with a current source and a parallel resistor. Again, that could be an impedance. And the nice thing about the Norton resistance is it's equal to the Thevenin resistance, and the nice thing about the three of them is that the Thevenin voltage is equal to the Norton current times the Thevenin or Norton resistance. The upshot of Thevenin and Norton's theorems is we can replace parts of a circuit with one or the other thing, right? If we have a circuit that has a voltage source in series with a resistor, we can replace that with a current source in parallel with the resistor, with the same resistor. Okay? And that's what's called source conversions. Okay, we've done that, and I just want to quickly talk about maximum power, and then we'll go for another break.
Could you repeat the last part on source conversions, please?
Sure. So the thing is, if I have a, let's give an example. If I have a circuit like this, right, I can actually replace that piece with something like that. Right, so I've replaced my Thevenin voltage source and series resistance with a current source and a parallel resistance, the same parallel resistance. And sometimes that makes the circuit a little easier to analyze if you can do that. And again, the three things all follow that equation. So if you know what VTH and RTH is, it's very easy to find IN, the Norton. And the Norton resistance is equal to the Thevenin resistance. Okay? And before we go to break, maximum power. Right, so here we've got some sort of a source, and we've got a circuit driving a load. So here's our load resistance, here's our circuit's resistance, here's our voltage. And the question is, how do we get the maximum power dissipated in our load? Because oftentimes that's what we want to do. You could think about this as your cable, right? And this as your set-top box. And you get better reception on your set-top box, even with digital, if the set-top box gets the most power it can, right? Because usually the thing that determines signal quality is a thing called signal to noise ratio, and the more power you have in the signal, the easier it is to poke above the noise. And I'm not going to go through the derivation again, but for maximum power, we want R equal to the load resistance. And if we're talking cable, the impedance, it depends on exactly the sort of cable your cable company is using, but they probably have coaxial cable, and the normal sort of numbers for the impedance of coaxial cable is 50 ohms, 75 ohms, or 110 ohms. What that means is the manufacturers of your set-top box, your cable box, need to make sure that the input impedance of their set-top box matches the numbers that the cable is from the cable company. Okay, so I've gone through the bulk of these things. I haven't talked about impedance much yet. I'm going to talk about impedance and transients next. But let's go for a break. Does anybody have any questions before we go for maybe a 15-minute break? Okay, if not, let's put the 15 minutes up, and I will see you on the other side. I'm going to go get some more coffee.
not taking a break. It's pretty much indistinguishable from them taking a break.
A touch of civilization.
Okay, hopefully I remember to unmute this time. Third time lucky. And let's see where we are. So I was noticing earlier that there is this three-phase circuits that we have on here, and I haven't mentioned anything about those, so I might talk just a tiny bit about them. But let's start at the top first, right? Operational amplifiers, ideal operational amplifiers, right? So ideal, and I call them op amps, right? So an op amp looks like this, maybe, right? It's got two inputs, a positive input and a negative input, and it's got an output. And because the two inputs are positive and a negative, it's often called a differential amplifier. Right? And the thing is, if this is V1 and this is V2, then V out is, for any operational amplifier, not just an ideal one, it's going to be equal to, the output is going to be some gain K, K is the gain, times the difference between the two voltages. And what makes it ideal? Well, to make it ideal, a few things happen. One, K is infinity. Okay, the gain is infinite. Even on a real device, it's possible to have that gain of the order of 100,000, 50,000, 10,000. So infinity isn't stretching the truth too much. It's stretching it a little bit. One of the upshots of that is that if one of the inputs to the device is connected to ground, there's the idea of a virtual earth, right? If V2 is connected to ground, then V1 cannot differ from V2 So effectively, virtually, V1 is also connected to ground. The third thing is that the input currents I1 and I2 are equal to 0. There's no input current required. Again, that's not true on a real device, but on a real device the input current is of the order of probably less than microamps, probably more like nanoamps, depending on the device. And because of those three things, we can do some rather funky stuff, right? I'm going to swap the polarities. If we put an op-amp into a circuit like this, right, where this is, I don't know, let's just call that C2 and this one C1, right, then the relationship between the input and the output is determined by the ratio of Z2 to Z1. Let's just quickly hop over here. Right, so here's the inverting amplifier. Oops, I want to go there. Right, so here the output is going to be minus Z2 on Z1 times Vin. So Vin is the voltage in here. So if Z1 and Z2 are just resistors, it gives us a way to control the gain. A negative gain, but still a way to control the gain. But if one of Z1 or Z2 is an inductor or a capacitor, then we can have either integral or differential relationships between the input and the output. It used to be when you were making a control algorithm for a robot or for some other automated equipment, well, it still is actually, you want to do often what's called PID control, right? And that stands for proportional, integral, and derivative. Control, PID. And so it used to be before the advent of computers that could do all of this. They could do the sampling and then the analog to digital conversion and then digital to analog conversion. Before the advent of those, a PID controller was basically a little bit more complicated, but it was basically 3 op amps, maybe 4 to sum everything up, right? An op amp that just gave you gain, which would give you the proportional piece, an op amp that would give you an integral action, and an op amp that would give you the derivative action. Okay, so that was why. These days, if you're going to do PID control, you're probably going to do it using a digital controller. However, you often want to connect up measurements to your controller or to just your data acquisition system, right? And sometimes you need the thing you're measuring is too small to be measured by your measuring system. So you may need to do something like this, right? Put some gain, particularly with strain gauges. They're often generate very small voltages, and sometimes you're better off sticking those very small voltages and amplifying them using a simple op-amp amplifier. Okay, so we've got ideal operational amplifiers. Now let's go through capacitance, inductance, etc. So remember, for a capacitor, let's go with green again. I equals C dV dt. Oops. Right, where C is the capacitance. And because of the relationship, because when we talk about capacitors now, our voltage is usually of the form A cosine omega t plus theta. And because of the relationship between voltage and current is now a derivative relationship, but we're interested in AC or sinusoidal signals, should be an S, right? We get a relationship. We can think about just operating at a particular frequency, and we get that the impedance of the capacitor is just 1 on j omega c. Because of that derivative relationship, we get an omega out the front when we find the current, and then when we divide the voltage by the current to get the impedance, we get a 1 on j omega c relationship, provided we work with the voltages and current as phasors rather than just as time signals like I've written them here. And remember, as a phasor, the way we write that is just A angle theta. We elide or hide the fact that we're running at omega t, or at frequency omega. And just like with a resistor, right? VC equals IC times EC. We have an Ohm's law relationship between the voltage and the current. And again, these are phasors, phasor voltage and a phasor current. They look like constants, right? A angle theta looks like a constant, but really it's operating at a frequency of omega. Similarly, and I'll just draw the capacitor again, right? Similarly, inductors right, V equals L di dt. And again, we're running with the voltages or the currents as cos omega t plus theta. And for an inductor, our complex impedance is j omega L. and the inductor symbol is a coil of wire, because that's all they are usually. Capacitor symbol is two plates close together, and depending on the type of capacitor, that is all they are, but the physical relationship might look a little different. If it's an electrolytic capacitor, it's two pieces of foil separated by a gap and then wrapped up around each other. If it's a ceramic capacitor, it's a little different. If it's a tantalum capacitor or a polyester capacitor, it's also a little different. When we have impedance, right, we have a real part and an imaginary part, right? This part is the resistance. The X, the purely imaginary component, is called the reactance. And this thing here is the overall thing, including the J, is called the impedance. Reactance doesn't include the J. Okay, so I've talked about capacitance, I've talked about inductance, I've talked about reactance, I've talked about impedance, I've talked about sinusoids. All I'm going to say about AC circuit analysis is we can do everything we did with resistors: mesh analysis, nodal analysis, superposition, Thevenin, Norton, maximum power. We can do all of those things, but now with complex impedances rather than just resistances. So that's effectively what I mean when I say AC circuit analysis. Let's talk quickly about transients. Right, so the first part of this course worked with resistors and constant voltages and currents. That should be constant. The second part dealt with impedances and sinusoidal voltages and currents. Because the approach we took in the second part relies on steady state, right? Because we've got the derivative relationships between voltages and currents in inductors and capacitors, there's an implied differential equation there. And so we can only do that second part if everything is in steady state. So in between those two things is transients, right? And again, because of those differential relationships, differential equations, we get and I'm only talking about either resistive inductive circuits or resistive capacitive circuits. we get equations of the form, which we looked at just a little earlier today, right? K1 plus K2 e to the minus t on tau. And the way you solve that is you figure out the initial condition, you figure out the final condition, that tells you what K1 and K2 are, and then you figure out what tau is. And the only hard bit about figuring out what tau is figuring out what the equivalent resistance is in the final condition, because you may have to do a Thevenin resistance calculation if there's more than one resistor there. And tau is either R times the capacitance or L, which is the inductance, divided by the resistance. Right, so it's either RTHC or L on RTH, depending on whether the circuit has a capacitor or an inductor in it. I haven't talked about transients in circuits with both, well, with all three, resistors, capacitors and inductors, because for that sort of a circuit, that circuit will generate a second order differential equation, and the solution to a second order differential equation, if you remember your maths, is going to be a damped sinusoid. So in addition to a constant term, there's going to be an oscillatory term as well, an oscillating term at some frequency that's determined by the relationship between C and L. I'm not going to talk about use of LT spice. I think you're all pretty familiar with that over the labs. So I'm just going to quickly talk about three-phase circuits. So for a start, why would I be interested in three-phase circuits? Ooh, why did I get three answers? It looks like I've got, I might have my... Oh, I've got 3 copies running. Let's not do that. And 38940. So let's go with the last one. Michael Matthews, any thoughts about why we might be interested in three-phase circuits?
Can you repeat that one more time for me?
Okay, so there's a line here which says three-phase circuits. What do you think a three-phase circuit might be, and why would we be interested in it? No thoughts?
No, I'm not really sure, to be honest with you. I can't have a brain fart at the moment.
That's okay. It's towards the end of a long semester and a long class today. So let's see if somebody else... Jonathan Abando, any thoughts? Joel, why would we be interested in three-phase stuff? No idea? I saw you unmute. You're going to say something. No, I can't hear anything. Maybe your microphone isn't working. So let's Try someone else. Saray, how about you?
No, I'm not too sure.
Okay, so three-phase. So I'm going to have to talk a little bit of... Go ahead, yeah, sorry.
I was gonna say, is that kind of like when like a generator produces like an output of like 3 waves, to kind of make like a almost like a DC output? Is that kind of similar to that?
Well, it's not even DC, so let's... yeah, let's have a look at this. I don't know whether
Can I hazard a guess real quick?
Yeah, go for it.
The only place I've really heard of it is in like big motors. And from my understanding, it's like they have all the phases out of sync just enough. It's by like just enough so that each time one hits its lowest point, another is hitting its highest. So they're all offset by, I think it's 60 degrees. So, to keep like larger motors running more efficiently. I could be
right. So
a little out of line here.
you've got the general idea, but if you go outside and if you have a look at, maybe you call it a telephone pole, maybe you call it a power pole. It's usually got both on it around here anyway. Around my house, they've usually got the cables for the cable companies, and they've got the Eversource power. And if you look closely, you will see that there are probably more than 3 wires up there. But if you look closely, you'll see that 3 of the wires are really close to one another. Right? They're rather not really close to one another. They're really similar in setup. And this is an example here that I just found from a picture on the web. I was going to try and take a picture out of my window here, but because it's spring, all the leaves are in the way, so it's a bit hard to actually take I'd have to go outside to get a decent shot. Yeah, these 3 wires on this example picture here are 3 different phases, and it's like it was said earlier. The 3 phases are generated from rotating machinery. Let's have a quick look, right? So what happens in the main power companies is they have generators, right? They've got gas-fired generators, they've got nuclear generators, they've got coal-fired power stations. There's wind, there's solar. Solar's a little different because solar doesn't use rotating machinery in order to generate stuff, but wind certainly does. Those big rotors are going round and round, right? And they're rotating something, and what that something is basically a 3-pole rotor. And this is a simplistic, bad drawing and a simplistic explanation, right? But each of those poles, funnily enough, are 120 degrees out of phase. Right, because there's 360 degrees in a circle. So they're 120 degrees out of phase. And the voltages that those rotating machines generate, we can draw them as phasors. Right? And I've drawn that badly, but again, each of these each of these phasors is 120 degrees out of phase. Okay, so that's what three-phase is. And if you go outside and you look at your power pole, you will see that three of the wires being strung from pole to pole have a similar look about them. They'll have similar isolators. These things here, they're round isolators. And what these wires have the voltage, or probably possibly higher than the voltage that is going to your house on them, right? And you don't want that voltage to touch this metal pole. This is a metal pole, I think. It might be a wooden one, but certainly the arms, I think, are metal. So you don't want those to touch. So what these things here are, these things here, they are insulators. They insulate the pole from the wire so that you don't get the power on the wire shorting down to earth. Like if it were raining, there would be a link or a low resistance path if that were connected. So these insulators insulate the wire from the pole, and you can see these connectors here from one side of the insulator to the other. They're just making sure that there is a connection from one side to the other. Now, one thing we haven't talked about, and I don't believe it's on the exam, but we'll have to check that. And if it is, we'll take it off. Is associated with this sort of three-phase circuit are a series of connections, right? And one sort of connection for three-phase circuits is like this. And the other sort of connection, and I'll draw it upside down from what I was going to. The other sort of three-phase, oops, that's too long. The other sort of connection is like this, right? And this sort of a connection is called a delta connection because it looks like the Greek letter capital delta. And this one is called a Y connection because it looks like the capital letter Y. And I've written it W-Y-E because I think it's usually written that way. And the interesting thing about these two connections is that you can convert from one to the other, right? So there are things called delta Y conversions. Okay, so that's what three-phase is. It's to do with the power. And as somebody said, you know, if you've got a sinusoidal signal, each of these phasors is a sinusoidal signal, or is representing a sinusoidal signal. But each of them is 120 degrees out of phase with all the others. And the reason it's 120 degrees out of phase is because it was generated like that, right? It was generated from a rotating machine which had three poles, and the three poles are 120 degrees out of phase. Okay, So that is my tiny bit about three-phase circuits. And I'm done. Does anybody have anything else you want to talk to me about, or you want me to talk to the class about? Okay. So, in that case, leave it there. Let's leave it there. Thank you very much for. Okay, it hasn't been an in-person, but thank you very much for an enjoyable semester. Please go and do your course evaluations. We've got 7 out of 25. As you can see, I'd like to get at least 50%, so the response rate circle there is green. So please give... I'm just getting a question about the peer assignment again. Oh yeah, we could do that. Let's have a look. So I think I said, yeah, I didn't mention it, Joel. So I apologise for that. Some people saw it. Spring 2021 assessment. Right, so I put out on Blackboard this thing, and the idea was that I think you had about a week to, well, maybe it was a bit longer than a week, but about a week to have a look at it and submit it. And basically it was a 3 questions about the different sorts of questions that we've had a look at recently, but using impedances. And the idea with peer review is that you do the assignment, and then once the submission time is over, you then get to review one or more other students' work. And I think I saw that, wherever it got to, it's under course tools, that's right. Right, I think I saw that 4 people had submitted. Right, so Stephen, Alexander, Ryan and Andrew had submitted something. So you'll each get a chance to review 2 of the, I set it to 2 of the other people's assignments, and basically grade them using a rubric that I think I put together. I've forgotten how to see that rubric. And the idea is just, one of the problems with doing everything online is that you're all dispersed. Whereas if I do this normally in an in-person class, then you're sitting beside each other, right? And you learn by osmosis, if nothing else, just by being close to one another. And the thought with the peer review was that you could then see what other people are doing in terms of how they solve problems. And I probably should have used these much earlier than I put them together. Okay. As it is, only 4 people submitted. If those 4 people do the review and submit their reviews of the other students' work, I'll give them a 5% bonus on the overall for the course.
Is this the bonus assignment?
This is one. The other bonus assignment is I've forgotten. There it is. So the other bonus assignment was to yeah, Joel, it's just for extra credit. It's not for a homework grade. And the other bonus assignment is to go and find a grounding point either on a power pole near you or on the outside of your house or building where you live, and take a picture with something written indicating in the picture that it's CET236.
Oh, okay. So there's two bonuses, or only one?
Well, at the moment, only 4 people are going to be able to do the or have done the peer review bonus. And
because I only saw this one, the one that you're showing me right now, because I didn't see the other one.
Right. I didn't really say much about it. I think I mentioned it briefly during one of the lectures, but I didn't mention it with much enthusiasm or fanfare. So the people who did it just saw it and did it based on seeing it in Blackboard. Okay.
Okay.
So Stephen's asking, do the course evaluations actually do anything for me before you besides giving you feedback? So it's a hard question to answer. There are, if I were a tenure track or a tenured person, well, no, only tenure track, then I could use the course evaluations as evidence to get tenure. Because I'm only an adjunct, that doesn't matter to me. So if there's I use it to get information about what I can do better, and other people can see it if they want, but it really doesn't have a huge amount of impact. If they were really bad, right? If I were a terrible lecturer, I would. That would be a way to force a bad lecturer out. But I don't think I'm that bad. I'm not. I have room for improvement. But I think I do an okay job. I cannot reopen the peer review submission because it's already into the second phase of review, and I thought about doing that, Stephen, but it won't let me, so no, I can't do that. Can I change the due date for homework 9 to tomorrow? Yes, you know I can. Will I? Yes, I will. So let's go and do that. Mehul Kumar, where is it gone? Homework 9, let's make it due tomorrow. So that is the 9th. And the 9th. And I need to go to WebWork and fix it there as well, don't I? Is that right? Yeah. Actually, I don't know. I don't know whether do I need to fix it there? I think I might have made it still doable on the 15th anyway. Yeah, I think I changed them all to the 15th. I'm only going to update them if you've selected them for your second chance assignments or your resubmission assignments. But okay. That's about it. Any other questions? I think I've dealt with all of those questions in the chat. Okay. Remember, you need to book your final if you haven't booked it already. I don't think everybody's booked it yet. Please book it. If you can't find a time that works for you, please email me and we'll see if we can find out. If you do email me, tell me times that suit you, 3 or 4 during the week, different days, different times, just so that we can get some overlap. You will find I am very, very, very busy over the next week, right? So let's see, my next week. That is my next week. Everything in orange is a student exam. Okay, so in fact, some of them I haven't set up for to be orange, so they've come in since I last had a look. So let's just make them exams, right? So that's next week, and then it trails off after that. But after that, I've got other stuff I need to be doing. Okay, so let's leave it there for today. Thank you very much for an enjoyable semester, and I'll see you at the final, and have a great summer regardless.